Hey guys, so in today's lecture, we are going to discuss energy from tides. So, as the chapter proceeds of ocean energy, we have seen how we can get energy from the temperature difference, the thermal energy which is stored in the ocean by absorbing the radiation of the sun. So, now we will see how we can generate energy from the tides, that is from the tides of the ocean. So first we will see the principle, and then we will see various systems through which we can generate the energy. So first we will understand why tides are caused. So tides are caused by the combination of attraction of sun and moon on the waters of the revolving globe, because the globe is revolving and its attraction, both of combination of sun and moon, the tides are caused. So once ocean tides are, we can say ocean tides are periodic rise and fall of ocean water level occurring twice in each lunar day. Rise and fall of water occurring twice each lunar day. So every day there will be a rise and a fall of water. So the tides are periodic vertical rise and fall of ocean water. The tidal rise and fall of water is accompanied by periodic horizontal to horizontal to and fro, means forward and backward motion of water called tidal currents. These are called tidal currents. This is called tidal currents. So due to this rise and fall, there is a to and fro motion, that is tidal current. The tidal current flow in horizontal direction have kinetic energy. This tidal current have kinetic energy. So this energy is called tidal current energy. So this is called tidal current energy. So the period between consecutive high tides. So the period between consecutive high tides is 12.5 hours. That is, if there is a high tide, then after 12.5 hours, then again we will have a high tide. The speed of the tidal currents is in the range of, so the speed is in the range of 1.8 kilometer per hour to 18 kilometer per hour. So these are the speeds of the tidal currents in which they are moving forward to and fro. Now we will see a tidal range. Suppose let's draw a graph. Suppose y-axis, x-axis. Suppose on the y-axis we have water level. This is water level. So this is the base we are selecting as water level, and above it there will be high tide and below it there will be low tide. So, and this is, suppose on the x-axis we are having a time period. It is a lunar day. So lunar day exists of a 24 hour and 50 minutes. So lunar day is 24 hour and 50 minutes. That is moon day. So there will be a high tide, then low tide. It will go according to the sine curve, high tide and low tide. So this is one tidal cycle. This is one tidal cycle, and this is the second tidal cycle. So in a full lunar day, we will have a two complete cycle tidals, a complete tidal cycle. So the upper point we will call it as A, and the lower point we will call it as B. The rise and fall of the water follows a sinusoidal curve. It is, it follows a sine curve. It is called a sinusoidal curve. The point A, this is indicating high tide, and point B, this is indicating low tide. And the tidal range R is the difference between consecutive high tide and low tide water levels. So R is equal to high tide level, that is A, minus B. So this is R. This is R. So that is A minus B. So now we will see. So as we have plotted the graph of tidal level versus a whole lunar day, that is 24 hours and 51 minutes, 50 minutes. So now we have plot a lunar month graph, that is for whole 29 days and 51 that is hours. So 29.51 days, so 29 days and 12 hours around. So what we have seen, so in full lunar month we have various. First is a new moon, then the first quarter, then there is a full moon, then there is a third quarter, and then again it is a full moon. So lunar consists of 24 hours and 50 minutes, and in one lunar day there are two low tides and two high tides. The effect is maximum when Earth, Moon, and the Sun are in one line. Since the Moon is nearer to the Earth than the Sun, hence Moon has greater contribution in formation of the tides. The surface of the Earth facing, so if we draw the Sun Moon system, so suppose Sun is in the middle, and suppose we are drawing suppose four phases, so 1 2 3 4. So this is Earth, suppose Earth, 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 and suppose this is Moon in one direction. Suppose Moon is in this direction, Moon. So we are considering all the four cases. So Moon, and suppose Moon. So here there is the pull of the Sun, and this is the pull of the Moon. Similarly, here there is the pull of the Sun and Moon both, and here is the pull of the Sun, and here is the pull of the Moon, and here is the pull of the Sun, and here is the pull of the Moon. So when the Sun, Moon, and Earth are in this same direction, that is they are in all the same direction, in one line. So hence the moon has greater contribution in formation of tides. The surface of the earth facing the moon experiences greater force of attraction than the surface away from the moon. So that is this surface, the surface which is facing the moon will have greater effect than the other surface which is not facing. So the force of attraction of the moon is 2.6 times than that of sun. So the force of attraction of moon is 4.6 times that of sun. So the force of attraction causes acceleration of water and earth towards the moon. So the water is getting accelerated the uh, towards the earth or towards the moon. The mass of water shifts towards the moon. Thus ocean water on the moon side experiences high tide, and on the other side experiences low tide. So here it will experience high tide and here it will experience low tide. Such daily tides are called the diurnal tides. Diurnal, urinal, diurnal tides. The diurnal tides include two low tides and two high tides for one rotation of moon around the earth. Now during full or new moon, when the sun, moon and earth are in a line, the gravitational forces of the sun, moon are enhanced and the tidal range is large, and the tidal range is maximum on the full moon and new moon, and such tides are known as spring tides. So here as you can see, on the new moon, on the full moon and again on the new moon, the tides are high. These are known as spring tides, and the tidal range is minimum on the first quarter. The tidal range is minimum on the first quarter and the third quarter of the moons, and such tides are known as neap tides, NEAP. So the tidal power is proportional. So tidal power is proportional to the square of tidal range. Hence, sites having more average tidal range, about 5 meter or more, are preferable for tidal power plant. So for tidal range greater than 5 meter are preferred for tidal power plant. So this is the concept of tidal energy. So how tides and tidal energy works. Now we will estimate the tidal power in a single basis system. So how much power it can generate, this tidal power in a single basis system. So I will draw a diagram. So for single basis system, suppose we are constructing a dam. So this is suppose a dam, and this is the area A. This is the basin. This is turbine. And suppose this is the height from the basin H, and suppose this is the tide range. So this is suppose high tide level, and suppose this is the low tide level. Now we will define some uh, variables, that is suppose this R is the tide range, R is the tide range, H is intermediate depth, and DH, this is DH is small change in head, DH is small change in head. A is surface area of water, M is equal to mass flow of water through turbine, rho is density of water. So now if we are considering an elemental thickness of water dH at a height h, okay, so we want to find for whole tide range. So the work done by the water, dW will be equal to, that is dm into g into h. So but what is dm? Mass, small mass. So mass is equal to, that is density into volume, that is minus rho a into dh. So if we apply this mass in the formula of work, so the dW will be equal to minus rho a g h dh. Now the total theoretical work during a full emptying is obtained by integrating the equation. So we will integrate this equation, W will be equal to 0 to R dW, so which is equal to 0 to R minus rho a g h dh. So if we integrate, we will get rho a g h square by 2, and the limits are from 0 to R. So our work done will be rho a g r square by 2. So this is our work done. So it is evident that the work potential is proportional to the square of tidal range, that is R. So the power is the rating of doing work. The average theoretical power delivered by the water is W, and divided by the time it takes each period to repeat itself. So the average power will be, so power is work done upon time. So there is work done upon time. So the tidal cycle between high tide and low tide is around 6 hours and 12.5 minutes. So which is equal to, T will be equal to 12.5, so T will be equal to 6 hour and 12.5 minutes. So if we want to find in seconds, if we count in seconds, it will be 6 into 3600 plus 12.5 into 60. So T will be equal to 22350 second. So P average will be equal to W upon T, that is rho g a r square upon 2 into 22350. So assuming, if we are assuming the water density rho is equal to 1025 kg per meter cube. Then P average upon area A, P upon A will be equal to 1 by 2 into 1025 into 9.81 upon 22350 into r square. So P average upon area A will be equal to 0.225 r square watts. So the P average, that is power, directly depends on r square, that is 0.225 r square, and this is the constant 0.225. So we'll see few examples using these equations also that were asked in this GTU, and this is the estimation of tidal power which we can gain from the tides. So I hope you understood these equations, and you will see uh, other systems also, that is this was a single Basin system, and we'll see other double cycle ebb and tide cycle systems. So thank you very much. Hey guys, so in the last lecture we have started a new topic in ocean energy chapter, it is tidal energy. So in tidal energy we have seen that various high tides and low tides during the various seasons of the moon due to the attraction of the moon and sun. So we get high tides and low tides. So in a full lunar day there are two total cycles in which you get two high tides and two low tides. So we also seen a whole lunar month how we get high and low tides. So then we have seen that the tide power is directly proportional to the range square. So that we have seen with the help of tidal power in a single basin system. So in this single basin system we got the formula that power P average upon area A is equal to 0.225 r square watts. So based on this based on this equation we will solve one example which was asked in GTU. So this is an example: a tidal power plant of single basin system has a basin area of 25 into 10 raised to 6 meters square. So area is given, the tide has a range of 10 meter, so R is given, the turbine however stops operating when the head on it falls below 2 meter. So that is small r is given. To calculate the energy generated in one filling process in kilowatt hour, if the turbine generator efficiency is 75% and density of water is 1025 kg per meter cube. So let's list out the data. Area is 25 into 10 raised to 6 meter square. Then range R is 10 meter. Then the turbine stops operating when the head It falls from 2 meter. So 2 meter is the head. Then calculate the energy required in one filling process in kilowatt hour. So how much energy is required in kilowatt hour if the turbine efficiency is 75% and density of water is 1025 kg per meter cube. So the total theoretical work W will be equal to from capital R range to where the turbine stops working is minus rho GA into HDH. So this will be equal to 1 by 2 rho GA R square minus R square. So the average power will be work done upon time. So that is, as we know, that is rho GA R square minus R square upon 2 into 22350. So average power will be 1025 into 9.81 into 25 into 10 raised to 6 into 10 square minus 2 square divided by 2 into 22350. So the average power P average will be equal to 1943.568 into 10 raised to 6 kilowatt hour. So considering the turbine generator efficiency of 75%, so P actual will be into 0.75, so will be 1457.676 into 10 raised to 6 kilowatt hour. So this is the power which is required for filling process. So now you will see various types of tidal power plants. So which are the various tidal power plants which we can install to get this energy from the tides. So to utilize the tidal energy, water must be trapped at a high tide behind a dam or barrage and then made to drive the turbine as it returns to sea during low tides. So the available energy is proportional to the square of the amplitude. So the main components of this tidal power plant are first dam, then second Slews Base, and third Powerhouse. So the function of the dam is to form a barrier between sea and the basin, or between one basin to another basin in case of multiple basin, and the most suitable word for the tidal power plant is barrage. So barrages have to resist waves whose shock can be served and where pressure changes continuously. The second component of tidal power plant is sluice ways. So the sluice ways are gates control devices. So they are used to fill the basin during high tide or empty the basin during low tide. So in existing plants, vertical lift gates have been used. Sledge gates can also be used. The flap gates allow only in one direction of the sea to basin, therefore the level of basin rises. The third component is powerhouse. So in powerhouse, turbine, generator and auxiliary equipments are the main components of this powerhouse. So that is turbine, generator and auxiliary equipments. Large size turbines are used because of low head available. Kaplan turbine with variable pitch blades, bulb type turbine or rib type turbines are more commonly used. Tidal power plants are classified on the basis of basins used for power generation. So there are only two types of uh, basins, that is first single basin system and second double basin system. So we will see one by one both. So let's start with single basin system. So first single basin system. So this is the simplest system to generate tidal power, and the single basin scheme have only one basin. So the basin is separated from the sea by a dam. So the sluice way is opened during high tide to fill the basin, and the turbine generator units are mounted within the ducts inside the barrage. And the single basin operation of tidal power plant will show in this in following figures. So the single basin system can be classified into three system. That is, first is so we will just draw the plan. So suppose tidal plant operation. Slews Base turbines. This is suppose C. This is basin. This is sluice base. This is turbines. So suppose now we construct a dam. So this is the plan. This is the top view. So now let's see the front view. So suppose this is a dam. So suppose this is the high tide. This is C This is high tide, and suppose this is reservoir filling. Reservoir filling. Now suppose we have low tide, that is ebb tide. So in that case, so the sea is filled from the reservoir back. So in that case, what will happen? So similarly, we are drawing the diagram. So there's a dam. So if there's a low tide and the reservoir is full filled, so the water will move from reservoir to the sea. Same diagram. So this is low tide or ebb tide. This is sea, reservoir emptying. So sluice gates are shut turbine operation section. So when the flood tide, that is high tide, comes in, the sluice gates are opened to permit the sea water to enter the basin or reservoir. While the turbine sets are shut, the reservoir thus starts filling while its level rises till maximum tide level is reached. At the beginning of the ebb tide, the sluice gates are closed. Then the generation of power takes place when the sea is ebbing, flowing back to the tide, and the water from the basin flows over the turbines into the lower level of seawater. So turbine are keep working until the rising level of the next flood tide, and the falling reservoir level together reduces the effective head on a turbine to the extent where it can no longer work safely and efficiently. The turbine are then closed and the sluice gate opened again to repeat the cycle of operation. So this is how the tidal power generation works. During high tide, reservoir is filled. During low tide, the reservoir is being emptied. So during the low tide, the turbine is being rotated. So this was the first single ebb cycle system. So now we will see the second single tide cycle system. So in the single tide cycle system, the generation, so in single tide cycle system, the generation is affected when the sea is at flood tide. So here, as we can see, that the generation was done at the ebb tide, but here the generation will happen at the flood tide, that is high tide. So the water of the sea is admitted into the basin over the turbines. As the flood tide period is over and the sea level starts falling again, the generation is stopped. The basin is drained into the sea through its sluice base. The ebb tide has a long duration than flood tide. The ebb operation provides an increased period of actual work. So it has been estimated that energy produced by an system ebb cycle system can be as much as 1.5 times the tide cycle system. The tide cycle requires a deep reservoir Thus, it requires greater construction costs. The main disadvantage in both ebb cycle as well as tide cycle is its intermittent nature of operation. So, generally, ebb cycle is preferred than the tide cycle. So, this cycle is not preferred. So, now we will move towards the double cycle system where at the both ebb and tide power is being generated. So, that is third double cycle system. So in double cycle system, the reservoir turbines are installed and power is generated during filling and emptying the basin. So the filling process occurs when the ocean is at high tide and while the water is in the basin is at low tide. So the emptying when the ocean is at low tide and the basin as a high tide. The flow water in both direction is used to derive the reversible turbines. Each turbine drives the generator into this system, and also continuous generation of power is not possible because short duration interruptions in the turbine process. So electric power is generated during two short periods during the tidal period of 12 hours and 25 minutes or once every 6 hours and 12.5 minutes. So the working has been explained of the double cycle where the both high tide and low tide power is being generated. So this was the single basin system. So in that we have seen different categories of cycle, that is single ebb cycle, single tide cycle and double cycle system. So in the next lecture we will see double basin system and various site requirements for tidal power plant. So hope to see you in the next lecture. So thank you very much.